Hello and welcome back. In this video, we'll continue talking about default adjusted expected bond returns. Previously, we talked about the transition probability matrix, which shows how bond ratings change with varying probabilities across periods. And in this video, we'll take a closer look at cash flow vectors, which are an important component of default adjusted expected bond returns. No mini exercise in this video. But we'll consider a bond. Actually, let's look at the spreadsheet we've been working on in the other tab. We've got hypothetical 3-year bond that will compute the default adjusted expected return for, right? So it's a 6% bond. We'll assume annual coupon payments, 3 years until it matures, right? Face amount of 1,000. So if all the scheduled 3 coupon payments and face amount get paid without the bond defaulting, we could compute the return that we would earn on a bond like this. And actually at a price of $925. If you pay $925 and hold the bond till it matures, and it makes all the scheduled coupon payments and the face amount payment at maturity, the return that you'd earn on that bond investment is actually equal to the yield to maturity. But bonds default sometimes, and we earn a significantly smaller cash flows than we initially expect. So how do we adjust for that? That's the whole point of this chapter, right? So we talked about the transition probability matrix as one ingredient into this model, and then cash flow vectors at each point in the bond's life are another key component. So let's talk about that. The cash flows I receive from a bond are a function of whether a bond is maturing, right? If it's prior to maturity, I just receive a coupon payment in a given period. Otherwise, when a bond matures, I receive the last coupon payment and also the face amount back. And then also the cash flows I receive are a function of whether or not the bond has defaulted. So let's look at that in matrix notation, right? We'll compute a cash flow vector for each point in the bond's life, right? Each tick on the cash flow timeline. And so the cash flow vector in our model has 4 rows. Each row corresponds to the cash flow that an investor would receive at each of the 4 credit ratings. Remember, A and B are the 2 solvent credit ratings, and then D denotes a cash flow when a bond is in default in a current period, and then E denotes that a bond has defaulted previously, and so you don't receive any cash flows after the default period. So let's compute these for the example in the spreadsheet that we just looked at. And let me just make everything fit here. So here's a 3-year bond, a 6% coupon rate. So in year 1, right, this area that I'm highlighting here would be a cash flow vector at time t equals 1. And so what cash flows would I receive across the 4 credit ratings? Well, they're described here, right? If a bond is rated A at year 1 and it's not in default, I would receive a coupon payment of $60, right? The coupon rate, Q, times the face amount, F. So a $60 coupon payment. And actually, let me make these absolute cell references because we're going to copy and paste this formula down. So a bond with a B rating in year 1 would also pay a coupon of $60, right? And then if a bond defaults in year 1, and we'll work with the transition probability matrix to evaluate that probability, a bond defaulting in year 1 would just pay the recovery amount, remember, which is a function of the recovery rate, lambda, and the face amount. So in this example, if a bond defaults in any period, the recovery amount is 45% of the face amount. So we assume that, if the bond defaults and the firm is liquidated, bondholders receive 45 cents on the dollar. So at a rating of D in year 1, a bondholder would receive a cash flow of $450. And then always, if a bond is rated E, it's already defaulted and we receive 0. Okay. So here's the cash flow vector at time 1. The cash flow vector at time 2 would look very similar because if the bond's not defaulted in year 2, for a rating of A and B, bondholders would receive another coupon payment, right? And then if a bond defaults in year 2, we assume as bondholders, get paid the recovery amount, lambda times the face amount, right? And then if a bond is rated E in year 2, that means it's defaulted in year 1, right? So if a bond is rated E in year 2, it's already defaulted previously and we receive no cash flow in that event. So those are the 2 cash flow vectors before the bond matures. When the bond matures, we'll use this version of the cash flow vector, right? Because when a bond matures, if it's not in default, I'd receive the last coupon payment, which is a function of the coupon rate and the face amount, like before, plus the face amount when the bond matures. And so this area I'm highlighting here looks like the typical cash flow pattern for a bond, right? Coupon payments before the bond matures, and then when the bond matures, one final coupon payment and the face amount at maturity. So those cash flows would happen, that cash flow would happen at the two solvent credit ratings, A and B. If a bond defaults at maturity, it doesn't make the final coupon and face amount payment, and it pays out the recovery amount in this model. And like we said, if a bond is previously defaulted, then the cash flow is 0 in the current period if a bond is defaulted in prior periods. So those are three cash flow vectors, right? The three cash flow vectors for the bond. What cash flows do I receive at each period depending on what the bond's rating is? So that's going to be an important component of computing a bond's default adjusted expected return. In the next video, we'll combine these cash flow vectors with the transition probability matrix, pi, which we've previously discussed, and then also one other simple matrix, and we'll combine all those things and get a way to compute a bond's default adjusted expected return. So, see you in the next video. Thank you.